Hallo, it's dumplet here. Here's an item on number theory. Find all positive integers m such that the floor, or the greatest integer less than or equal to m squared over 4, is prime. Now this item came from DAM 2022, an exam that dumplet has hosted. The link to the PDF file will be in the description. As usual, pause this video if you'd like to give this item a try. But if you're done, let us dive into the solution. Alright, so there is a standard way to kind of approach these questions. So the floor of a certain thing, well in this case m squared divided by 4, and that is to consider different types of values for m. Now what do I mean by the types here? Because it's going to be different depending on the question. Now here I'm going to propose that we're going to consider different values of m under mod 4. Now mod 4, because the denominator here is 4, and although it might not be obvious as to why we have to consider different values of n under mod 4, but once I show you the examples or the cases under mod 4, it might be a little bit obvious now. So, well, obviously under mod 4 we're going to have 4 possible residues, 0, 1, 2, or 3. So we could write m as something else. So m, I could write it as 4k, right? That's gonna be the 0 mod 4k, so it's a multiple of 4. Now I could also write m as 4k plus 1, m as 4k plus 2, and m as 4k plus 3. That's gonna be the 1, 2, and 3 mod 4 cases. But I propose we are not gonna write it this way. I'm gonna write this a little bit differently. I'm gonna write 4k plus 1 as 4k minus 3. I'm going to write m as 4k minus 2. And I'm going to write m here as 4k minus 1 for the 1, 2, 3 mod 4 cases, because I just want to say that in all of the cases here, we're going to consider k to become a positive integer. Because m is a positive integer, so k here should also be a positive integer. Well, at least we're simplifying our cases along the way. All right, so let's try to take into consideration the possible cases now. So I have 4k, 4k minus 1, 4k minus 2, 4k minus 3, as you can see here, but let's just do the cases one by one. And you guys will probably understand the motivation behind considering different types of values of m under mod 4. All right, m equals 4k, that's going to give you m squared to be 16k squared. And then if I divide it by 4, so taking the floor of this one, that's going to be floor of 4k squared. Now k is a positive integer, so 4k squared is definitely an integer. It's going to be just 4k squared. And well, 4k squared, based on the number itself, it's a multiple of 4 already, so this is never prime, all right? That's always composite, so no possible cases here if m is a multiple of 4. Next, let's try to consider m to be of the form 4k minus 1. So this is the 3 mod 4 case. Now, if m was 4k minus 1, we can try to take the square of that. Whoops, wrong color. 16k squared minus 8k plus 1. And then we have to divide it by 4. Now, I'm going to split these, like this fraction into 3 different fractions. Into their respective... I'm going to split this fraction, that's what I meant. So 16k squared over 4, that's going to become 4k squared. So 8k over 4 is 2k, so minus 2k, and then we add a 1/4 over here. All right, now here is kind of the application now of the floor function, because I have 4k squared minus 2k, and I know that's an integer. And I'm adding 1/4 to an integer, so obviously it's not going to reach the next possible integer yet. So this would just evaluate to 4k squared minus 2k, right? Because it is greater than 4k squared minus 2k, but it's not to the next integer yet. So because of that 1/4 here is just less than 1, right? So we have 4k squared minus 2k. We could factor a 2k out, so 2k times 2k minus 1. All right, now if we want this to be a prime number, we know that one of these two factors must be a 1, right? Now 2k minus 1 is smaller, so I think this should be the candidate for a 1. Now, if 2k minus 1 was a 1, let's try to solve. 2k minus 1 was equal to 1. I'll simply get k equals 1 here. And substituting k equals 1 into the kind of format that we have here for m, we're going to get m here to be 3, right? We can always try to substitute m equals 3 here. M squared is 9, so 9. So floor of 9/4, that's going to be 2, and 2 is prime. So we have no problems here. But for the case of 4k minus 1, so the 3 mod 4 case, we only have m is equal to 3, right? So that's 2 cases down. Let's try to do the other 2 cases. All right, let's just say m is of the format 4k minus 2. Okay, so squaring 4k minus 2, we're going to get 16k squared minus 16k plus 4 divided by 4. All right, it is divisible, so we just have floor of 4k squared minus 4k plus 1. And, well, this is just an integer already because 4k squared and 4k, they're just integers. So 4k squared plus 4k plus 1, the floor of that is just 4k squared minus 4k plus 1. And this is pretty obvious to be a perfect square. So, well, no prime numbers are perfect square anyway, so this case is just impossible. All right, now finally we have the m equals 4k minus 3 case. So let's try m equals 4k minus 3. By the way, this was the 2 mod 4 case, and now we're considering the 1 mod 4 case. So if m was 4k minus 3, take the square of that. So 16k squared minus 24k plus 9, and we're dividing it by 4 again. Again, we're going to do the similar trick as we did here in the 3 mod 4 case. We're going to split it into individual fractions. So 16k squared over 4, that's just 4k squared. 24k over 4, that's 6k. And then 9 over 4, well, that's just 9/4. But I'm just going to write as 2 and then plus a 1/2 because I want to put the, 2 and a 1/4. Because I want to say that, well, this part is an integer. And we're just adding kind of 1/4 to an integer. It's not going to reach the next integer yet. So the floor of this one would just be 4k squared minus 6k plus 2. Now this is actually factorable into 2 times 2k minus 1 times k minus 1 actually. All right, pretty interesting. We have a lot of factors. Now, since we have a 2 here, the only possible case where this entire thing is an integer is when both 2k minus 1 and k minus 1 are equal to 1. Now, unfortunately, that's impossible because they are 2 different values. Now, if they're both equal to 1, I'm going to get 2 values for k. That's impossible. So, once again, for this case, we won't have any possible values for m of the form 4k minus 3, right? Because if I were to try to make 2k minus 1 equal to 1 and k minus 1 equal to 1, again, they must be 1 because they cannot be negative because k is a positive integer. So that's going to give you contradicting values because I have to have k equals 1 and k equals 2 at the same time, but we know that's impossible, so that's why we don't have cases here. All right, so after exhausting all possible cases or all possible forms of m, apparently we only have one case, m equals 3, that's under the 3 mod 4 case. So logically speaking, we can conclude that the value of m squared over 4, the floor of m squared over 4, it's prime, only when m equals 3, right? M equals 3 giving the prime number 2 for the value of m squared over 4 and then taking the floor of that. And this will be our final answer. Hopefully you guys learned something new from this video, and I'll see you in the next one. Bye bye!